Hey, welcome, buddy. Alrighty, we're going to start a little early here. Apparently, there's some other stuff going on tonight, and I don't want to have people's attentions divided or conflicted on what they want to watch, even though it's YouTube. You can watch this later. This probably won't be very long. A couple preliminary things. One, a friend of mine got me a new coffee maker the other day, Black & Decker, real nice unit, and some 3-time triple coffee strength stuff. I've had 2 cups. It's potent. So if I'm a little wired right now, I apologize. Not really. It's good stuff. But hopefully to get me through this mathematical stuff, I'll need the coffee. So let me just get that right out of the way. Second of all, I'm going to try to do this justice. Now, I haven't really done formal proofs that much. I mean, never really had to. In calculus, you have to do some, but not of any real degree like doing a formal proof. And so the reason I'm doing this is a couple of different reasons. One, well, actually, make sure that the audio levels are right. So if you're going to hear me just fine, let me know. The reason I'm doing this, a couple different reasons. One, I see out there in the internets that people that tend to not understand these types of concepts, that argue against objective math, and I call them objective math denialists. That's my term for a person who denies math. Like if you say 1 + 1 = 3, you're an objective math denialist because 1 + 1 = 2. And this is something that could be demonstrable. And I find that the people that have these intellectual misconceptions tend to also have them in other areas, like they're flat earthers, they're young earth creationists, they're anti-vaxxers, they're anti-maskers, they're climate change deniers. There seems to be a unifying theme amongst these people that refuse to accept facts. And I mean facts. And what I mean by a fact is something that cannot be false. A fact must be true. These are mathematical facts. There is just no question about it. There is no debate about it. There's no arguing about it. There's only people can explain it and people can understand it, or they can't understand it. There's no argument to be had on it. It's just none. And I use this particular mathematical thing as a litmus test. And the litmus test demonstrates to me about what's called virtue epistemology, having the virtue of being open-minded and not intellectually isolated. Because if somebody refuses to accept a mathematical fact, then how are you going to get them to change their position on anything that's subjective or otherwise? So this is one thing that I've used for many years to determine the kind of person that I'm having a discussion with. Another one I use is Monty Hall problem, which I'll have a separate video on, even though I've done before, but that's one of my favorite. So as you guys know, this comes up all the time. It's on Twitter right now again. If you guys don't follow me on Twitter, which you all do, but if you don't follow me on Twitter, it's in the video description. But this proof right here is a formal proof from Josh Garver, who is a mathematician, great guy, huge supporter of my channel. Very, very decent gentleman. And he's smart. He's smart. And he wrote this proof, and I went over it and found nothing wrong with it. There's a couple different kinds of proofs out there. There's a constructive proof where you try to find an example of what you're trying to demonstrate, right? If you can find an example of something, then it's called a constructive proof. There's a non-constructive proof where you don't actually find an example of something to prove it. And then there's like the direct proof. This is the direct proof. So what he's setting out to do is say, okay, by this, then I can prove this. Okay. Now I know a lot of people that don't understand math are going to be like, well, you're starting with a definition. Yes, this is the definition in mathematics of something. Things are prescriptively defined to some degree in mathematics. Okay, they start with axiomatic assumptions, and you can have certain mathematical definitions. Okay, so what I'm going to be doing is going through this. I'm going to show it in Wolfram Alpha as well a little bit. Hopefully we get the concepts across, because I thought to myself, in order to show how this proof actually works, you kind of maybe have to step back and say, okay, does a person understand the concepts involved? And are they that difficult? No, they're not. They're really actually not. This may look like a complicated proof. It's not that complicated. No offense to Josh. It's not a complicated proof. It just looks a little intimidating. And what I think I want to do is maybe explain it, hopefully, in a way that I can get across that you don't need to be intimidated by looking at something like this. There is a way to learn this language and figure it out. Now, again, I don't do formal proofs, and it's been a long time since I've really looked into this kind of stuff. I mean, I have an understanding of it, but it's been a while. So bear with me. Josh is actually just now tuning in, I think. Yeah, he's out there. And hopefully if I make any errors or mistakes, he'll correct me, because that's what people do, right? I mean, if you flub something, you want to get it right. You want to get it corrected, so that's fine. So if you guys out there that do know math, if you see or hear anything that doesn't make sense or is wrong, just let me know and I'll correct it. Which, by the way, math is objective, right? Somebody, no offense to Josh, but Josh had a little tiny error in his original proof. Somebody noted it and said, hey, I think you mean this. And Josh was like, yeah, I mean this. Let me fix that. Why? Because it's objective. He didn't sit there and argue for 5 years of his life. Oh, you're wrong, poopy head. I'm going to stalk you for 5 years of my life and attack you personally because you show my math is wrong. No. So that's what I like about math, is that you can actually show that it is objectively true, and if anybody looks at it, they can go look at it. That's what we mean by objective, okay? So this is about 0.999 equals 1, or 0.99 repeating equals 1. And the same thing as 1/3 equals 0.333. A lot of people have a misunderstanding of that particular problem. They don't seem to recognize that 0.99 repeating is a symbol. It's just a symbol. That's all it is. It's a signifier. It represents that nomenclature, that symbol, right? That symbol represents the number 1. It represents the position. 0.99 repeating represents the position midpoint on the range of 0 to 2. So what's the halfway point between 0 on the real number line and 2? Well, it's 1. So 0.99 repeating is at the same exact position on the real number line as 1. They are the same exact number. There's no difference between them. It's not rounding. It's not math magic. It is a mathematical equivalency, merely because that is how a limit of a sequence works, which is a foundation of mathematics. I mean, this right here is a foundational concept of mathematics, of how numbers are constructed is based upon these types of concepts of determining the limit of a sequence or the summation of a sum. Now, I will probably do a separate video on summation of the sums and partial sum summations. I've done videos on summations before, and I've explained summations. So if you want to go look at my playlist under math, you'll find a video about summations where I give a very brief, generalized overview of how a summation works. But I'm going to get into how to do an infinite summation video, I think, one of these days, and then explain how to do a sum of a series, not a sequence, but a series. There's a difference. But a sequence is this. A sequence is something where you have a real number being produced in the field of R by a order of numbers that usually could be represented in some closed form, such as, let me you know what? Let me just start off like this. Let me instead of just jumping in that, let me go to Wolfram Alpha real quick and just kind of show you what I mean by this before we jump into the proof. So if I had a series or sequence, sorry, of something like this, okay, and you might intuitively, you already probably know if you don't know math, but you still probably already know where this is going, okay? Okay, so that sequence 2, 4, 6, 8, 10. You intuitively know that the next one's going to be 12. I believe most people can figure that out, right? That's a pretty simple sequence. Just like 1 plus 1, n plus 1 would be the formula for sequence of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? So for all the terms given here, this is the closed form, which means that it can be described with just a single, no, not a single, but a formula where the variables equal something. So you'll see a lot of closed forms in quadratic equations, like the what is it? You'll see it in the form of a squared plus 2ab plus b squared, right? Or no, it should be, sorry, a squared plus b squared. Yeah, no, that's right. And so this sequence, you'll see that formula just for the terms given, where n is some natural number, maybe my natural number, maybe 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? I could use that formula for any n, any number in n, capital N, which is the symbol for natural numbers, and come up with the next in the sequence. Okay, for n equals 1, I get the number 2. For n equals 2, I get the number 4. For n equals 3, I get the number 6. For n equals 4, I get the number 8. So every time you add 1 to n, you'll get that sequence. And when you see a summation, you usually see an index, and it'll say like n equals 1 to infinity. And what they mean by that is you're counting n from 1, then you're adding another one, and then you add another one. So it's n equals 1. What do you get? N equals 2. What do you get? N equals 3. What do you get? So that closed form equation will give you that sequence, right? So that's what we're trying to determine, but it gives you it here, right? So if I have the sequence, let's do this one, 2, 4, 8, 16, 32. Let's try that one. This would be 2 to the n. Okay, so now it's an exponent. So if I have n equals 1, it's 2. If I have n equals 2, it equals 4. If I n equals 3, 8. And for any n, I could figure out what the number is in the sequence. So I could tell you right now by using this sequence, by using this form, okay, 1, 2, 3, 4. My fifth, n to the fifth is going to be 64. It's the next number in the sequence, right? That's what a sequence is. So given 0.99 repeating, you have this sequence here. Okay, so that's the sequence, 0.9, 0.99, 0.999. That sequence, if you take the limit of that, is going to converge on a specific number, which is going to be 0.99 repeating, which is actually equal to 1. I should recognize this. Sometimes Wolfram Alpha does. You have to put it in a form it knows. If I try this. Yeah. I don't think it likes this part. I don't know, the working with sequences on Wolfram Alpha, it does, you have to put it in, like I said, in a form it knows, but what am I doing wrong there? 0.9. Hang on. I'll get it. Yeah, there we go. All right, so this is the sequence here, 0.9, 0.99, 0.999 equals 0.99 repeating, okay? So this sequence is a repeating decimal, right? True. So this sequence is this, and you can figure out what closed form would be for that. It is 9 over 10 to the nth, but this is what Josh is using in his proof kind of thing. He's going to be using a definition of a sequence, of a limit of a sequence to be specific, to show that this equality, this true, must be the case, okay? So that's what we're going to do here. So let's dive into that. All right. So in this proof here, he starts off with, in any calc book, you'll see something similar to this. It says, a definition, a sequence, A sub n, okay, that's a sequence, is said to converge to the number A provided that for every positive epsilon, there exists a natural number n such that, and we'll get into the formula there. So what this is saying is an epsilon is some arbitrarily small number that is close to 0, but not 0. Okay? It's not imaginary, but it is arbitrary, and it's extremely small, close to 0. Okay? So it's saying that for any number you can find, there's a convergence between the absolute value of that sequence, which I showed you on Wolfram Alpha, minus a, which is going to be the number that it converges upon, to be the limit of the sequence, is less than epsilon for all integers, or all, in this case, all integers and all n is going to be the same thing, because integers are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and here n is equal to 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, for any value in the set of natural numbers, which again is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So for any n you pick, you'll have to be able to find a difference between the sequence and the limit that's going to be less than some arbitrarily small number. Okay? And I can tell you right now, if there is no arbitrarily small number between two values, those values must be identical. Okay, there's something called the trichotomy property, which says that x is either less than n or excuse me, x is either less than y, x is greater than y, or x is equal to y. And for every number, every rational number, x plus 2 divided by 2 will give you another number if those numbers have an inequality. So if x and y differ and you divide by 2, you'll get another real number. You just, for any two numbers you pick, there's always going to be a subdivision, right? You can always bifurcate that. However, if the numbers are the same, there's nothing between them. What's the difference between 5 and 5.0? Well, there is no difference. So they're the same number, right? So there's no number, there's no epsilon that's so arbitrarily small that's close to 0 but not 0 that exists between the numbers 5 and 5.0 because they're the same number. Here's the same thing. There is no epsilon that exists between 0.99 repeating and 1. And so this is the definition of a limit of a sequence. It's the absolute, it's called absolute convergence. The reason why it's called absolute convergence, because there is something called contingent convergence, where you might have a sequence that contingent convergence. So it might contingently converge to something, like for an alternating sequence or a, or actually it'd be more of an alternating series, I guess. A sequence can't alternate because it has to be in an order. Well, no, I guess it could. Yeah, no, it could be in order. It doesn't have to be, yeah, no, I guess it could alternate. Yeah, because you can alternate a sequence and alternating series. So if you have something that alternates, it goes back and forth, but the absolute value doesn't, then it's conditional. It's a conditional convergence. I should say contingent. It's a conditional convergence. But a unconditional, or a what's called absolute convergence, means that if the absolute value of the sequence minus the limit that it converges to, then it says that is a convergence sequence. That's what he's testing for. He's saying, does this sequence minus the limit of the sequence, is it less to epsilon for all numbers he can find? That's what he's arguing. Okay, so the sequence 10 to the n minus 1 over 10 to the n converges to 1. That's the theorem. That's what he's trying to demonstrate, right? He's trying to demonstrate that that holds in all cases. Yeah. Yeah, conditional convergence is more of a series thing. Yeah, it's not a sequence. Yeah, you're right. Somebody pointed that out. It is a conditional convergence would be a series. Yeah, I don't think a sequence can conditionally converge, but that's only going to be if the absolute value doesn't meet the, like for a telescopic series, I've seen it, and a, what is it, a alternating series, right? So when you alternate, if you got like 1 plus 0 plus 1 plus 0 plus 1 plus 0, those things, weird things happen with that kind of math. So that's where you get like 1 plus 2 plus 3 plus 4 plus 5 equals negative 1 over 12 r. And not r doesn't mean r reals there. It means, and I hate this guy's name. I'm going to butcher his name. I can never pronounce his name. People know who he is. It's that math guy. But that's called analytical continuation. So that's not what we're talking about. But you can use analytical continuation to evaluate a telescopic series or a alternating series. All right, that's a fun side note. But thank you on that. All right, so that formula, 10n minus 1 over 10n. Let's put that actually into Wolfram alpha and see what we get on that. I will change it over to Wolfram alpha. 1 second here. You hear me typing? All right, so let me change it into Wolfram alpha again. All right. This should be. All right, so what he's trying to find out is if this sequence with this forms, when n increases each time, goes to 1. Okay, so let's put a value in here. Let's start. Your index is going to start at 1. So let's put a 1 in there. Let's see what we get. We get 9 over 10. Okay, well, 9 over 10 is 0.9, right? So that gives you the first number of that sequence, right? So if the index starts at 1, so if n equals 1, and you're going to add incrementally 1 to n in step by step, in incremental steps, right? Because we're dealing with natural numbers here and integers, so they're going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So if we put 1 in there, we get the first number in that sequence. Okay, great. That formula seems to work. That's the sequence. That's going to be the formula for the sequence. We're going to put 2 in here. Kawasa of 5001 says, as I understand, mathematical proofs are absolute and axiomatic, and there's no way one can look at it sort of wiggling out of it. Correct. Yeah, no, yeah. For the reals, right? For the reals, there's a set of axiomatic suppositions and presuppositions and assumptions that exist to construct the reals. Now, if you're dealing with some other, field, and I don't mean like field as in dominion. I mean field as in mathematics. Like you have group, you have a ring, you have a field. A field is a something that holds, if I remember, under what's under addition, under multiplication, abelian, and so there's certain conditions to make a field. And you can make another field that's not the reals, where you could make a mathematical relationship. For example, if I just had 0, 1, 2, 3, and I used that and made the field out of that, you can make it where it would be like 1 plus 1 equals 0. I've done that before in another field, another video. When I had Dr. Trailer on, we were talking a little bit about Galois theory, but we didn't really get into it. It was more matrix. But you can show that by changing your field, you can make a matrix where you would have, for 0, 1, 2, 3, you would have 1 plus 1 equals 0. But that's a different field, right? That's not the reals. You're dealing in an entirely different set of mathematics. Okay, so, oh, wait, you know what? I didn't mean to change that. I made a boop there. All right, so the second value. So as n increases, it goes to 2. I get the next number in that sequence, which is 99 over 100, which is 0.99. The next increment would be 3, right? Because I'm going step by step. So the next one is going to be 0.999. Okay. You see where this is going, right? So this formula is what he's trying to show. All right, so he wants to say that if you continue out n to infinity, if you did this iteration an infinite number of times, which, by the way, we cannot do in finite time. You cannot do an infinite amount of things in finite time. So what math allows you to do is fake it. And somebody's going to say, look, Steve's faking math. No, what basically that means is we just, we in math, we can make something such that we can say, okay, if theoretically we could do this for infinite amount of times, what would we get, right? We can do it in one step, right? Zeno's paradox is an example of that, right? If you fire an arrow toward a target, at some point in time, that arrow has to be halfway to the target. And then it has to be another halfway. And then it has to be another halfway. That is a sequence. That is 1 over 2 plus 1 over 4 plus 1 over 8 plus 1 over 16 plus 1 over 32 plus 1 over 64 and so on. And you can figure out the next one's going to be 128, 1 over 128. But eventually, that arrow hits the target, right? It doesn't keep going half and half and half and half and half and never reach it. It reaches the target. If an arrow, when you add that sum of the series 1 half plus 1 quarter plus 1/8 plus 1/16, if you add them all together and you get 1, you're adding an infinite summation. And you're just doing it like that. You're doing it instantly almost, right? You don't have to do every step to figure out an infinite summation. That's one of the beauties of math. You can actually figure out what it would be if you did have enough infinite time to do these mathematical calculations. But we know the arrow does hit the target, right? So if the sequence is 0.1, 0.9, 0.9, 0.99, 0.999, we know that sequence is going to converge and hit a target. The target it hits is 1, or 0.99 repeating. All right, so going back to his theorem. So we know this is the formula that he wants to demonstrate. Proof, let epsilon equal 0. So what he's saying here is, okay, I'm going to pick some randomly, arbitrarily small number, but it's greater than 0. Okay? Doesn't matter what that number is, right? It's just some small value that's greater than 0. Now we need to find a number of n as an element of n such that. So he's saying he wants to find a natural number that is in the set of n. So 1 is a natural number, that's in the set of n. 2 is a natural number, that's in the set of n. You'll see when you see a double struck thing like that, then you know you're dealing with some kind of set. Q is would be double struck Q would be for rationals. Double struck R is for reals. Double struck I is for imaginary. Double struck C is for complex. And there's a couple others, obviously, but that's what that means. So this double struck actually has a denotation to it. it denotes that that represents the entire set of natural numbers. So he's just saying there's some natural number in the set of natural numbers that exists, okay, or okay, that he's trying to find actually. So this formula right here is going to be, again, similar to the closed form notation that we had before, that I've shown in other places, but I'm not going to get it now. But how you would the formula for figuring out 0.99 repeating. It's basically 9 over 10 raised to the n kind of thing. Okay, and if you take a summation of that, you're going to get, if you add up all the partial sums, you get 1. So this is going to be less than n for all integers. N is greater than or equal to n. So for any number he picks, this is going to be less than epsilon. So if you actually look at Wolfram alpha again, we're gonna oops, why did I do that? Back to Wolfram alpha. I want to show you guys something. What we're really conceptually trying to do. Let me put it back on the screen. Okay, there we go. So if you notice here, if I actually took and I put 0 here, hopefully this works, right? If I did have the 0 here, no, that's not it. No. No, that's not going to work. All right. So yeah, it's going to be n, I guess. So if you, what it is if n was a theory, an infinite thing, you're going to end up with 0.99 repeating over 1. Okay, minus 1, minus 1. You would end up like this if you did the actual series or sequence. So this is what you would actually end up with. Okay. Is that right? No. I think I had it right before. I'm messing up here. Because you're trying to find, you see it's less than 0, less than epsilon, right? Yeah, let me change that. Go back. Hang on, let me go back to here. Because you want to find this to be less than 0, because this is going to be 0.99 repeating minus 1 over 1 minus 0, and 1. This whole quantity on the left-hand side is equal to 1. So that 1 minus 1 is 0. So the absolute value of 1 minus 1 is 0. So 0 is less than epsilon for all integers, n is greater than or equal to n. Does that make sense? I a little butchered that, and I apologize. This is saying that this equals to 0 is going to be less than epsilon. That's it. So for any number you pick, this is going to be less than some arbitrarily small number, less than, greater than 0. It's arbitrarily greater than 0. All right. So he says, notice then, this quantity here, and he just does simple math here if you think about it. What he does is he takes this quantity here, minus 1, and then he takes 1 and he just changes it to 10n over 10n. Well, that's 1, right? 10 raised to the n over 10 over raised to the n is equal to 1. So minus 1 here, he's just changing it by making common denominators. That's it. That's it. I mean, that's, again, people look at these things and they see it's so complicated. It's not. He's just changing 1 and he's just rewriting it in the form of a over a, right? But in this case is a common denominator. Well, if things have a common denominator and you try to subtract them, you can do that. Okay, so he just subtracts the top from the bottom. Well, 10n minus 10n is 0 minus 1 over 10n. So you end up with minus 1 over 10n. So far, this is easy. This is easy. By the way, are you seeing my mouse? Maybe that's confusing because you're not seeing my mouse, are you? Oh, yeah, I think you are. Okay, so, and then when you take the absolute value of this, the absolute value of any negative becomes positive, correct? Right? So he's just removing the absolute value of that. And so the absolute value becomes 1 over 10 to the n. In fact, if you go, OBS should be able to, yeah, okay, so if you look here, when you take an absolute value, like I said, you're always going to get a positive number. Always, 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 always. Matter of fact, when you take the square root of something, you always get a positive value. There's only one primary square root of something. And you'll notice this tells you right here, by the way, if you look here, R-E-N, that just means real, by the way. So this gives you the real result of something, because there is an imaginary component in some cases, right? But you don't want the imaginary component. And if it says, I think it's IM for imaginary where it says RE. If you see IM, I think it is, that means imaginary. But RE, it means this is the real component. So if I have a complex number that's in the imaginary that says A plus BI, A would be the real part of that, and BI would be the imaginary part of that. So for any modulus Z, you can actually determine what your real and imaginary components are. Okay, so that's why you have that funny little RE down there. Just a kind of a fun side note. All right, we're going back to the proof here. Now he's saying that for any value you pick for n, that's always going to be less than 1 over n, and that's just intuitive, right? Square root is always positive, yes. Square root is always, the primary square root is always positive, Icarus. Now you say, well, wait a minute. You know, if I have the square root of something, it produces possibly 2, positive and negative. Yeah, but for a square root, it's always going to be just the primary. So the square root of 4 is 2. The square root of negative 4 is 2. Now, what are the roots are a different question, right? But obviously, negative 2 times negative 2 is 4. But when you're looking for a square root, you can only get one primary. That's it. So you don't say the square root of 4 is 2 or negative 2. You just say it's 2. Okay. You can't have a negative for a square root. It just doesn't work. All right. So this is kind of intuitive, right? Because if n equals 1 here, then 1/10 is less than 1 over 1, right? Yeah. You know, if n is 2, then 1 over 100 is less than 1 over 10. Or 1 over 2. Whatever n you pick, this value on the left-hand side is going to be less than the right-hand side. That equality holds. Okay? For all numbers in the natural numbers. Right? That makes sense, right? I mean, for any value you pick, that 1 over 10 to the nth is always going to be less than 1 over n. Pick it. Try it. Figure it out. If any n, pick one. Right? It's always going to be less. And by the way, somebody out there is probably going to say, well, what about n equals 0? Remember, natural numbers start usually, in most cases, 1, 2, 3, 4, 5. Now, some people argue that 0 is a natural number. I don't put 0 in the set of natural numbers, but here it is for all integers n. All integers n, where n is a element of n is going to be starting at the index 1. Okay, so in his proof here, the index starts at 1. So 0 is not in play here. You cannot put 0 in here because he's starting at n equals 1. And the natural numbers, because the natural numbers he's using is 1, 2, 3, 4, 5, 6, 7. You know, blah, blah, blah. 0 is not in that set. Okay. Okay. So now that gets kind of interesting. Now by the Archimedean property, which I've explained on Twitter many times. By the way, he doesn't prove the Archimedean property, and nor does he have to. In a more rigorous, you probably would want to do something like that. But what the Archimedean property of R basically, in a nutshell, says is that there are no infinitesimals in reals. Okay? Now, some people argue that 0 is an infinitesimal. And that's fine. If that's how you want to view an infinitesimal, I don't have an issue with that, actually. However, I think it makes more sense by the common understanding that an infinitesimal is some value in R that is greater than 0, but infinitesimally small. Okay, it doesn't exist, you know, on the real number line. It's some arbitrary value though that is greater than 0, but the Archimedean property says there can be no infinitesimal on the reals. Okay? So there can be no number that is the next. Okay, so if I said to you, what's the number closest to 1 that's not 1? Right? Well, there is no such number, right? Because for any number you pick that's less than 1, you can, like I said, bifurcate it, divide it take that number, subtract it from 1, and divide it by 2 and get another number out of it every single time. So there is no last number closest to 1 that's not 1. Okay? If you think about it conceptually, that makes sense. There is no highest number next to 1 that isn't 1. And you can get into what's called upper bound and lower bound and supremum and all this other mathematical jargon stuff. But the reality is it's just very simple. you can't find a number. You can't say what's the closest number to 1 that's not 1. It doesn't make sense for the reals. And it gets into what's called the continuum hypothesis, or the continuation of the, or was a continuum of the reals, or you can find it called the well-ordered principle, or there's a whole bunch of different things that go to the compactness and denseness. There's all these mathematical jargon terms that even I have issues with. But it doesn't matter. You don't have to know the jargon. You just have to think about it simply and go, oh, wait a minute. There is no number next to 1 that's so close to 1 that you cannot subtract it from 1 and get some value out of it. Well, Icarus, no. The square root function has only one solution. If you look at a square root function, right, it only has one solution. There can only be one primary solution to a square root. Just like for like a linear equation, there's either 0, finite, or 0, 1, or infinite number of solutions for a linear equation. A square root function can only have one solution, period. It's not by convention you always take the positive. It only produces one solution. All right. All right, so Brian notes the Archimedean property is the important part. Yes, this is critical in this proof. You're absolutely right. As a matter of definition, 0 shouldn't be called infinitesimal. And I agree with you on that. I'm not a fan of it myself personally, but I don't have an issue with it when people do it for their own constructive mathematics. You'll see it a lot of times in constructive mathematics. But so, again, there's different types of maths out there, right? So you might see somebody consider 0 an infinitesimal. I don't. I think by definition, an infinitesimal must be greater than 0. It has some arbitrary value to it, but it's something that can't exist. It's so small it can't exist. It's kind of like, maybe I hate using a heuristic type approach like this, but maybe it might help people conceptualize it as for the science people out there, which I love science. Think about Planck's time, or Planck's second, 10 to the negative 43, or Planck square, or Planck anything. You cannot divide Planck something, right? What's less than Planck's time? Well, there's no such thing. It doesn't make sense to describe what it means to be less than Planck time. What's smaller than a Planck unit, right? If I have 1 Planck length, what's smaller than that? Well, you can't divide anything smaller than that. It makes no sense, right? And so think about it conceptually maybe that way, is that you can't have an infinitesimal so small in the reals that you cannot divide it by something. Anything you can divide in the reals if you have it less than a number. So anything less than 1, you have a number in between it. And you can do that process infinite number of times. That's not what you learned. You might want to check it out, Icarus. I'm not BSing you. I'm straight up with you. Square root only has one solution. I think you're thinking of roots, right? It has more than one root. It doesn't have more than one solution. Those are different, right? Remember, a function by definition, Icarus, if you recall, only has one solution, right? There's a one-to-one correspondence for a function. One thing in, one thing out. Remember? So a relation has more than one, right? You can have a relation that has more than one answer. But a function, for anything you spit into it, a square root function, which is a function, can only have one output. By definition, a function can have one output. Does that jar your memory on that? Does it make sense? Ben out there or anybody else, does that make sense? Let me know if that helps you conceptualize that the fact that a function must have a one-to-one correspondence. All right, so moving on here, because this is the critical part of this proof. Now by the Archimedean property R, we can now choose some natural number that's in a set of all natural numbers such that the natural number is greater than 1 over epsilon. So that arbitrary value that's greater than 0, because you can't stick 0 in here. Division by 0 is bad. Matter of fact, for the rationals, it is specifically defined such that you cannot put a 0 in a denominator, right? You can't have 1 over 0. Okay? So, in this particular case, you have 1 over some arbitrarily small number that n has to be greater than. Has to be greater than. Okay, and then he just rearranges that. He just changes the e from the denominator and puts it on the other side of the equation. That's all he's doing here. So he has one. Reformulating this to 1 over n is less than epsilon. Okay, so 1 over some value, 1 over n, 1 over 1, 1 over 2, 1 over 3 is going to be less than some arbitrarily small number that he picked from the beginning. It then follows that what he started with, this absolute value of what forms the sequence if n would go to infinity, which is 0.99 repeating. If you see this little thing on the left-hand side, this n to the 10 to the n minus 1 over 10 to the n, just think of it as 1. Okay, because if n went to infinity, this would be equal 1. So you have 1 minus 1, which is 0. So the absolute value of 0 is going to be less than 1 over n, which is whatever your value for n is. This is always going to be less than n, because 0 is less than 1, right? So if you have 1 here, right? Well, 1 minus 1 over 1 is minus 1 is 0. Well, actually, no, that'd be 9 minus 1 over, or no, wait, what is that? What if I pick 1 there? Let me do this real quick. I want to make sure I put this out right. No, it's not going to be 0, is it? Dang it. Let's see here, 1 sec. I want to make sure I get this right. I don't want to mislead you guys. That's why I like Wolfram Alpha and check this stuff. Yeah, 0.9 minus 1. All right, it's going to be 9/10. There we go. 9/10 minus 1. That makes more sense. Yeah, minus 1/10 is going to be minus less. Do I need to scroll down? Yeah, you have it here. Okay. Yeah, I'm sorry. I'm just kind of overthinking this, Josh. So this value here is going to be less than 1 over n, which is going to be less than or equal to 1 over this natural number. 1, 2, 3, 4, 5 is less than epsilon. For any value you pick, n is greater than or equal to n. So for any n you put in here, this equation, or this relationship, I guess you could say, it's not an equation, but this relationship is going to hold. For any value you pick, for n, this on the left-hand side is going to be less than 1 over n. Let's say you have n equals 1. 1 over 1, this over here is going to be less than this, right? If this is less than this for 1 over n, it's going to be less than or equal to 1 over n for any epsilon. Hence the sequence that this forms, if this one's to infinity, right? If n was 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, blah, 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 that converges to 1, because that sequence, as I started from the beginning, shows you that if you put a value in, you're going to get 0.9. You're going to get 0.99, 0.999, 0.9999, 0.99999, and ad infinitum. Right? So by doing that, yeah, it is 0. Yeah, okay. Yeah, I'm just overthinking it. I had to get the math right. Let me, if you put 1 in there, right? If you start off with n equals 1, you end up with 0, right? Because 1 minus 1 is 0. So 0 is less than 1 over 1, which is less than 1 over natural number 1, which is less than your arbitrary value that you started with. So 10n, where n equals 1, minus 1 over 10n is 1. 1 minus 1 is 0. The absolute value of 0 is less than 1 over 1, which is 1, which is less than 1 over a natural number 1, which is 1, which is less than some arbitrary value that must be greater than 0, right? Because we already said from the beginning, epsilon must be greater than 0 for any number you pick. Thus, that proves that sequence converges to 1. Because this is what he started off, with his theorem, that converges to 1 by this definition. And by using this definition, the sequence, 0.99 repeating, which is this on the left-hand side, right? The 10n minus 1 over 10n is actually a to the n right here. The a is the limit of the sequence, is this 1 right here. So the absolute value of a sub n minus a is this right here. That's all it is less than epsilon, which he proves down here. So what he started to prove, that this absolute convergence of the sequence minus the limit is less than epsilon for all integers n greater than or equal to n. And that's what he does right here. If you look at this equality, the sequence on the left-hand side here, minus the limit, which is the 1, a is the limit there, is equal to 0. 0 is less than 1 over 1, which is less than 1 over 1, which is less than some value, arbitrary value that's greater than 0 for any number you pick that is greater than or equal to some natural number, 1, 2, 3, 4, 5, 6, 7, 8, 10. There you go. That's the proof. That's it. You know what? I should have put it back on the proof there. Sorry about that. You should have told me I was just on Wolfram Alpha. So let me just repeat that once again by showing you visually. The absolute value of the sequence, a to the n, minus the limit, which is a, is less than epsilon for all integers of any natural number that's less than or equal to n, which is going to be 1, 2, 3, 5, 6, 7, 8, 9, 10. So if you go down to here, this left-hand side, 10n minus 1 over 10n, is a to the n. That's the formula for that sequence right there. Okay, so that sequence minus the limit of the sequence, which is 1, is equal to 0, which is less than 1 over 1. 0 is less than 1 over 1, which is less than 1 over n, which is 1, 2, 3, 5, 6, 7, 8, 10, which is less than some arbitrary value, that's epsilon, which is something greater than 0. So here it's saying 0 is less than epsilon for any number you pick. That's it. That's the proof. So, you guys got any question on that? Josh, did that explain it halfway? I haven't done an explanation on a formal proof in a very long time. So bear with me. This is the first of one in a very long time that I've explained something like this. So if I butchered it a little bit, I apologize. Wolfram Alpham's touchy. You got to get it just right. As I said, I am wired. So let me give it a minute for the video to update here on the live chat so you guys can weigh in on that. Josh, how did that do your proof justice? Did that explain it properly enough? How you were trying to prove that sequence, that formula for that sequence, 10 to the n minus 1 over 10 raised to the n, that forms the sequence 0.9, 0.99, 0.999 will eventually converge to 1. Meaning, by the way, that it's by definition, a different definition, but it's similar, that the definition of the limit of a sequence is defined by which the sequence converges upon, as n goes to infinity. All right. I didn't catch anything terribly wrong. I appreciate that. Yeah, no, minor stuff's going to creep in, like, minor math typo stuff, I'm trying to relate the concepts. So if I get the concepts right, I'm good to go with that. I'm not a mathematician, okay? That's why I do this. I'm not a mathematician. I just had maths before, but I'm not a mathematician. So if I can explain this in a basic way that somebody can understand it, then anybody should be able to understand this. It doesn't take a mathematical genius or a mathematical degree to understand this. It really doesn't. You just have to sit down for a minute and think it through. That's all. You said you're using the Archimedean property differently than I said? Well, I'm not sure how to use it then, because that's the only way I know about it. The Archimedean property, in a nutshell, is just there's no infinitesimals in ours. Yeah, it's a little more complicated than that. You're right, but I'm breaking it down to very simplistic terms that you just can't have an infinitesimal in R, right? Does that work? But all right, no questions, nothing. All right, well then we're gonna wrap it up so you guys can watch other things. If you guys find people that still argue that 0.9 and repeating is less than 1 or not 1, just have them drop by this video, minus the little flubs in mathematics. The conceptually, they should be able to say it. They should be able to explain it and understand it to somebody else. It's really not that hard. It really actually isn't. And this is what kind of is disappointing. When you have something that is so objectively true that you can actually literally prove. There's not much in life you can prove. But you can prove this. And you can prove things in mathematics. You can prove that the square root of 2 is irrational. You can prove, certain mathematical concepts. Even by definition, we know things to be the case, right? It's a mathematical fact that all squares have 3 triangles, right? It cannot exist any other way. So if somebody says, hey, a triangle has 4 sides, they're objectively wrong. There is no argument. There is no debate. There is no discussion. They are just wrong. Now, there's a discussion where you can explain it to them. You can say, look, all triangles have 3 sides. It is not possible to have a 4-sided triangle. At that point, they're just arguing poorly because they're not accepting facts. And at that point, they'd be an objective math denier. This is a fact, just like all triangles have 3 sides. The equality of 0.9 and repeating is 1. Same number, same exact value, no difference between them. One is just a different symbol called an infinite decimal expansion. The other is a terminating decimal, which is 1. But 1.0, 1, 1.00, 1.00 repeating all mean the same thing. So repeating decimals happen all the time. In any base, you're going to find a repeating decimal anyways. So people need to stop thinking that 0.99 repeating is some kind of ongoing process. I've even on Twitter like yesterday, someone was like, oh, it's approaching 1 but not reaching 1. No, it is a static number. It doesn't approach anything. It sits on the number line. It does nothing. Nothing. It's 1. The 1 doesn't move. 0.99 doesn't move. Or 0.99 repeating doesn't move. It is the completion of a function or a completion of a sequence that has been infinitely added up. Well, it's not even added up. That would be for a series. It's a limit of a sequence is what it is, right? So if you can infinitely take that sequence, 0.9, 0.99, 0.99, blah, 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 the limit of that sequence will converge to 0.9 repeating or 1. Same number. Kawasa says the problem is people arguing 0.9 repeating is not 1 probably are not going to be able to understand 2 seconds of the video, and you're probably right. However, this gives them the tools to go start and ask questions, right? Because I think most people could actually look at this proof and break it down if they want to and go, okay, this makes sense. Here's your sequence, A sub n. Just put in your sequence there. You could put in 0.999 repeating, because that's the termination of a sequence, minus your limit of your sequence, which is 1, is less than some value that's greater than 0 but not 0. Okay? But we know there's no number that exists there. We know the 0.9 repeating minus 1 is 0, right? But 0 must be less than epsilon, because we've already said epsilon is some arbitrarily small positive number. Yeah, and the whole, by the way, is zip 100, that whole 1 plus 2 plus 3 plus 4 plus 5, they explain that very poorly. That is a divergent series, right? It doesn't converge to nothing. It blows up to infinity. It only is minus 1 over 12 when you use a certain type of analytical continuation, and it's a special type of summation that you do. And again, I can't pronounce his name. Mama Jidijidion? Is that how you pronounce his name? Josh, you're going to have to pronounce his name for me. I don't hear these names too often. I just know what they are. But because I'm not a mathematician. But only in certain kinds of analytical continuation. Now, there is a reason for that, believe it or not. There are some types of analytical continuations that people will say, well, why do we have them if they don't represent, a standard way of doing a summation or something like that? Come to find out that some of those models actually do have real-world applications, one of which is actually in electron orbitals and quaternaries, I believe they're called. Quaterns. Quaternaries, octenarians. When you're dealing with like not just complex numbers, but you're dealing in even higher degrees of complex numbers, there's different things out there that can be used to model orbital mechanics. Yeah, Ramanujan. 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 We're going to call it that, Ramanujan. Well, at least you guys know who he is. So, yeah, don't mock my pronunciations because I suck at them. I admit that. But I know who he is. You know how long it took me to figure out Chandrasekhar? And even then I get it wrong. Like a Chandrasekhar limit. I butcher these names. I suck at them. So Cross says, it's probably an incorrect view, but I think they might understand it easier if you say 0.33 repeating is just a flaw in the decimal system that cannot accurately display the concept of 1/3. No, it's not a flaw, though. That's the problem. It's not a flaw. It's just, you could say maybe it's an artifact of the decimal system. It's a byproduct of the decimal system, but it's not a flaw of the decimal system. They would latch onto that, and it doesn't accurately, I think, explain the concept. But the easiest way to even think about it is we know that 0.111 equals 1/9, right? I mean, most people, I think, understand that. I mean, you learn that in, like, I don't know, elementary school, don't you? So what happens if you take 0.111 repeating and you times it by 9? What do you get? You get 0.99 repeating, which is 1. I mean, that should be able to understand that, I would imagine, wouldn't they? Let me see if I can do it this way real quick. I'm going to show you if I Yeah. Okay. So let me. So even if I show you here, let me go back to Wolfram Alpha. 1/9, 1/9 is 0.111 repeating. Right? I think everybody agrees on that. So 1/9 times 9 is 1, right? 9/9 is 1. So 0.1111 repeating times 9 is 0.99 repeating equals 1, right? I mean, that's just, it makes sense if people think about it, but I don't think they stop and think about it. See, 1/9 is equal to 0.11 repeating, right? You know, this is equal to this. Well, what's 9 times this? 9/9, which is 1. Which is 1. What's the decimal approximation? This. What's this times 9? 1. If 9 times this is 1, then 9 times this has to be 1, which is also the same as 0.99 repeating. What is 9 times the first decimal place? 0.9, 0.9, 0.9, 0.9, 0.99 repeating. That's as simple as it gets. I mean, you don't have to understand the proof that Josh did to understand that, I don't think. You know? 9 times this. I just got my live stream there. All right. Is there a way to solve Zeno's paradox? Yeah, that's been resolved by calculus years ago. Like I said, I mean, the Zeno's paradox is solved by the fact that you have an infinite summation, right? And I'll get into summations and partial sums in another video. But the fact that you can have 1/2 plus 1/4 plus 1/8 plus 1/16, that is what Zeno's paradox is resolved by, because you add all those things up, an infinite number of iterations, what do you get? You get 1, right? But that's, again, those gets more into the summation of series, which is a little bit different. I'll do a separate video on that, but just to show what it's like. This is what he's talking about. This is Zeno's paradox. So at time 1, you start off with at time 1, it reaches some midpoint between you and the target. So it's halfway there. Then at time 2, you take another bifurcation. You get 1/4 of that, then 1/8. So that by taking an infinite sum where n equals 1 to infinity, so each iteration you're increasing 1, for the formula or the equation of or not even equation, I guess, it's the expression 2 raised to the negative n, or 1/2n, equals 1. So 1/2n, for any value you put in there, you're going to get the sums here. So this summation of all these different terms will give you 1 if you did an infinite number of adding them up. So this resolves Zeno's paradox. Yeah, that's all. Yeah, you're just noting the convergence, right? Yeah, you're just noting the convergence. This series, this is not a sequence, by the way. This is a series. This series converges upon 1 if you take an infinite summation. That's it. Pretty cool, right? But that's a whole different topic. And I don't want people to confuse sequences with series, because I do that accidentally all the time, and I hate that. All right. So, all right, guys, I'm going to wrap this up. Go have some fun. It is the 23rd, so tomorrow's Christmas Eve, and the next day's Christmas. And I doubt if I'm going to stream. If I do, it's just going to be play games. I've been playing Gambits on Destiny 2 and Crucible matches. So if you guys want to do some gaming, Destiny 2 is a free game, and it's fun. And there's some other games we play. So message me if you want to be, in our little fire team, or if you want to play some other games. And just relax and enjoy your holidays. Been a lot of stress this year. 2020 sucked for everybody. I want to thank my Patreons. I want to thank the people that have joined as members to this channel. I want to thank my mods. Hey, look, Steve has mobs. My mods. And most importantly, I want to thank my friends. And all you guys are. And I mean that in the strictest sense of the word. You guys are my friends. Online or not, I consider people that I'm congenial with, that I talk to all the time, friends. And many of you actually are friends almost even, it's in real life, because, I mean, even if I hang out with you, it's a real life friend to me. I don't really know much more different than that. Just because I'm not in physical proximity with somebody, doesn't necessarily mean I'm not in real life friend with them. This is real life. You guys are my friends. All right. I think Icarus has one last question. All right, Icarus, what's your last question? Then we'll wrap it up here. Yeah, man, if 2021 gets worse, we're all screwed. I mean, what can happen? Zombie apocalypse, alien invasion, gamma ray burst. I mean, yeah, so many different things. I'm betting on the zombie apocalypse, but, we'll see. Brian says the modern Zeno is nothing going to have an infinite chain of causes. Yeah, well, that's a metaphysical question, right? The medical question would be, if you subscribe to the principle of sufficient reason and cause and action, which I don't think is actually a physical thing. I know people are going to get me on that, but I really don't believe in the law of causality in that degree. I think that's completely descriptive. I don't think there's any reason for it. I think it's assumed there's a law of cause and effect. I don't think there's a physical reason to actually say that is the case, other than we merely are describing something we see. But it still holds, right? We still see a cause and effect. But I believe there are causes or effects without causes, especially in quantum mechanics, like spontaneous nuclear decay or weak nuclear decay, especially, or spontaneous fission. They kind of happen without reasons. Now, I could get into some more of my own kind of ramblings about why maybe they might have a reason when you're dealing with some kind of virtual quarks that exist in the boson or hadron that somehow pop into existence near the boundary conditions, and it overwhelms the particle and kind of it splits apart. But that's for another day. I've been toying around with that on something that I was reading once. But long story short, yeah, they go into the Zeno's paradox as, okay, everything that's contingent must have a contingent cause. And so you can go back in this infinite regression of causality, of contingency, and you must end up either with some infinite regress, some infinite line of causality and contingency, which is called a brute fact that exists, or some kind of ground metaphysical necessity that exists. And a lot of times they'll call that God, right? That actually is called the argument from contingency. But anyways, okay, Icarus doesn't have a question. All right, Moon. I am Luna. Moon says for $9.99. Thank you. I appreciate that. We've all been hurting this year, so I appreciate people doing super chats. I really do. I've become a members. It's so appreciative. You don't even know. Happy holidays and love you, Steve. You are my friend, and likewise, we have been supporting of you. You've been supportive of us, and that to me is what a friend is, right? I mean, I don't have to know every detail about somebody to consider them a friend. It's just not how I operate. So I love you guys. And I'm going to probably just go play some games and enjoy your Christmas, enjoy your holidays, be safe. Don't anybody else die between now and the end of the year, okay? Have some consideration for us. If you're going to die, do it after the 1st, okay? Good night.